Okay, let's get going. A couple announcements. So the cap for the course was expanded to the size of the room, so I anticipate we'll be able to get people who were on the wait list enrolled soon-ish, in any event, well before the deadline. But you do have to put yourself on the wait list in order for that to work. If you can do it through SSOL, that's easiest. If you're not part of GSAS, you may have to fill out a registration adjustment form and take it to the QMSS office on the 8th floor of the International Affairs Building, and then give it to Megan. She'll email me, and I'll say it's like fine to put that person into the class. But do that, as soon as possible in order to minimize headaches with that. Also, on the syllabus. Oh, so a number of people have sort of emailed me whether you can audit. That's fine as well. You don't need to have any special permissions or anything to access the course on Canvas. That's readable by everyone in the world. So you can just go on there, get the syllabus, etc. If you weren't here on Tuesday, there's a part on the syllabus about class participation, much of which we'll do online via CampusWire. So there's a link you can click and a code to get added to the class. Remember that sort of good class participation is, considered asking a question or answering somebody else's question like once a week. And the first week is half over with already. And a lot of you haven't even signed up to CampusWire yet. So you couldn't possibly answer any of the questions that have been posted on there, even though there haven't been any yet. But you wouldn't be able to see the things that I post on there. And so that's going to be the primary way that I make announcements to the class. Questions about any of that stuff? Okay. So today we're going to be talking about probability. Like I said before, learning how to speak in the language of probability is an essential part of applying Bayesian statistics to a social scientific or other problem. And this is the area in which QMSS doesn't really prepare the students in the first semester to do something like this. So we're just going to dive in, go through things relatively quickly, but hopefully this will get us everything that we need in order to build on in coming classes and whatnot. Before building on anything, we have to talk about the disclosure. This is Columbia. I work at Columbia. You go to school at Columbia. I also use Stan, which is kind of a software of the class for business purposes, and that creates the appearance of a conflict of interest that you are required to know about before listening to the rest of this presentation, even though we're not going to be talking about Stan today. So you're required to know that there's a potential conflict of interest about math, pretty much. Okay, so the first thing that we need to, let me back up a little bit. The way I like to learn things back when I was taking classes is to just make sure I really understood the definitions of things. And if I could keep the definitions straight, I always thought I would be able to figure out what would be the relationships among the concepts, or what would be the implications of defining things this way. Now, I sort of have since realized that that's not the way everybody prefers to learn. A lot of people like to start with examples to sort of try to get the intuition of that, and I think that's inadequate over the long run for a class like this, because if you try to go, if you sort of de-emphasize the definitions and just sort of throw some examples out there, people sort of extrapolate back to the definitions in different ways, in ways that aren't really correct. So I like to start off first with the definitions, and then we'll throw up an example or two that utilizes those definitions as we go forward. So that's the style that may take a little bit of getting adjustment to. So the first thing we want to define is a set. So a set is a collection of elements, and those elements can either be intervals, like all numbers between 0 and 10, counting the ones with decimal places, or they can be isolated elements, such as, 1, 2, 3, and 4, or, small, medium, and large, something like that. One often used set that we'll be using not so much today, but a lot throughout the semester, is the set of real numbers. Now, some of you, not so much with the QMSS, have come from a background where you're taking legit math classes, and when people talk about numbers, they tend to mean complex numbers. I'm never talking about complex numbers. Do not have time for that. Talking about real numbers, subsets thereof, inclusive of the integers. So real numbers, loosely speaking, numbers that have decimal points, even if that's like a 0.000. The integers are a subset of the real numbers, namely the real numbers that can be written without any decimal points. And the set of real numbers is often denoted with a sort of empty R, and the integers often denoted that set empty Z. So if there's like a plus as a subscript or a superscript, that means a restriction of the real numbers to the positive real numbers, or at least the non-negative real numbers if we include 0 in that set, excluding all negative real numbers. So we'll see that sometimes. Sets can be categorical. We'll certainly see that when we get along into regression models and things like that. But today and next week, we're going to be focused on the integers or some subset of the integers as the set that we're going to be thinking about probability with. And then 2 weeks from now, we'll start talking about sets that have continuous intervals to them. Okay, so that's a set. What's a random variable? So first of all, we need to define or review what is a function. So a function is just a mapping from one set to another. It's a rule that uniquely maps each element of some input set to some element of the output set. The output set is often going to be the real numbers, but the input set could be integers or some subset of the integers or some subset of the real numbers. But the key thing about the definition of a function, distinguishing it from a mere relation, is that there has to be a unique mapping each element of the input set to some element of the output set. And a random variable is a specific kind of function. So there's functions in general, and then random variables are a restriction on that. A random variable is a function from some sample space, which is denoted omega, to some subset of the real numbers using a rule that's based on probability somehow. And so a random variable is a specific kind of function. So, here we see in this graph here a function defined by this curve. It's a mapping from the set on the horizontal axis between 0 and 1 to the set of the non-negative real numbers on the vertical axis. And you can see that this mapping is unique for each element in the input set on the horizontal axis. There's exactly one value of the curve on the vertical axis. So hopefully that definition of a function is something that you heard about before. But random variable is a specific type of function mapping to some subset of the real numbers with a probability-based rule. Now, I already mentioned this thing omega. So one of the things that I probably should have mentioned before when talking about probability, we tend to use a lot of Greek letters. This is the capital letter omega. Basically, you need to learn the Greek alphabet, both the capital letters and the lowercase letters. You can find that in the first part of the Math for Political Scientists book that we read from today, or on Wikipedia or whatever. If you just look at sorority houses, those are only the capital Greek letters, okay? You need to also learn the lowercase ones, all right? So the sample space, denoted omega, is the set of all possible outcomes for some, let's say, observable random variable. So everything that could happen. So if we have a random variable, a process, a function, of rolling a regular 6-sided die, no 12-sided die or anything like that, 6-sided die, what would be the sample space omega in this case? 1 through 6. All right. So it could be any of those faces could come up. Now, one of the things that's a little bit of a subtle distinction, you don't want to conflate conceptually a realization of a random variable with the function that generated the realization. So if I'm talking about a function, a process, that's rolling a die. And if it comes up 5, that's a realization, one particular element of the sample space. The 6 things it could have been, you know, it comes up one or the other of them. That's a realization of a random variable, not the random variable itself. The random variable refers to the function or the process that gives rise to a realization. Another thing that trips up people all the time, and it dates back to the days where people were typing on like typewriters, is to use a capital letter such as X to refer to the random variable, the concept, the function, the process, and the lowercase version of that, little x, indicates a realization of the random variable, capital X. So they didn't have real sophisticated typesetting back in the day, so they introduced this distinction between capital X and little x, and when you say it out loud, sometimes that gets a little bit lost if you just refer to X, but hopefully it will be clear from the context or from the slides whether I'm talking about the random variable, capital X, or a realization thereof, little x, from the corresponding sample space. Does everyone understand those distinctions? Good. Okay, bowling. So I really like this example because bowling is something that is simple enough for everyone to understand. I mean, the scoring of it is a little convoluted, but just like the physics of it, pins falling down, everybody can understand that. And yet it's rich enough to illustrate all the concepts that we need for probability with discrete random variables. So here the random variable is rolling a bowling ball, and you know, pins can fall down. So each frame of bowling starts with 10 pins upright, and then you get 2 rolls per frame to knock down as many pins as you can. So what will be the sample space omega for the first roll of a frame of bowling? 0 through 10. So you can roll a gutter ball or miss the lane entirely or whatever. Otherwise, score a 0 on that roll. And then anything 1 through 10 otherwise. Good. Okay. We're going to introduce the syntax with the vertical bar, and that is read as given. So the probability of some random variable taking on a particular realization given some other information. And so bowling is not something historically that social scientists were all that keen to apply quantitative methods to. And then after Bob Putnam wrote that book, everybody started analyzing bowling and stuff like that, including someone named Hone, can't remember her first name, who wrote a thesis discussing a few, along with her thesis advisor, discussing a few distributions for the probability of knocking down some number of pins, so that has to be non-negative, out of n. N is 10. And if you have a finite sample space, you can simply enumerate probability of knocking down 4 pins and knocking down 7 pins, etc. But a more common way of proceeding when we get a little bit farther along in the class is to specify a function that you can evaluate to tell you what that probability of knocking down 4 pins or 7 pins is. And one of the functions that's used in this thesis is based on Fibonacci numbers. And so the probability of knocking down X out of n pins, so given that there are n pins available, is equal to the ratio of the xth Fibonacci number divided by -1 plus the nth plus 2 Fibonacci numbers. And the Fibonacci numbers are simply defined as the sum of the previous two Fibonacci numbers, with the base case that the 0th Fibonacci number and the 1th Fibonacci number are both 1. And if you need some intuition as to why this might be a reasonable way to specify a probability function for bowling, as best I can do, it has to do with how the pins are arranged, like 1, then 2, then 3, then 4 in the back. And so that has some tendency among decent bowlers to produce a probability of, X pins falling down that's governed by this function here, the ratio of the xth Fibonacci number to the -1 plus the nth plus 2 Fibonacci number. So this idea of specifying a function that tells us the probability of a random variable taking on this or that realization, given some background information, is one that we're going to utilize over and over again over the course of the semester. So I just want to, introduce a simple one, relatively simple one, right here in the first week. So here's the list of the first 13 Fibonacci numbers. Again, except for the first 2, they're formed by summing the previous 2 Fibonacci numbers. And if you look at it, you might see that the sum of the first 11 Fibonacci numbers is 232, which is 1 less than 233, which is the 13th Fibonacci number starting from 0. And so that's where this -1 plus the n plus 2 Fibonacci number comes in the denominator. Basically, that equals the sum of the numerator for all the values in the sample space. And that's going to be important. So if you have your laptops, and you probably should, you can source in this function. I define a function f that computes the Fibonacci number. It does it without recursion, just because that's more efficient to evaluate it. It does it with rounding or whatever, but it's the equivalent way of defining Fibonacci numbers. So I have that function f there. No. Why did I get small all of a sudden? So I have this function f, which returns me a Fibonacci number. And then the probability of knocking down x out of n pins is given by this line here, which defines a function named PR. That function is a function of x, and it takes like a background argument n, which is going to have a default of 10 for the first roll in a frame of bowling case. And it's just going to return the probability. So it uses an if-else statement. So if x is greater than n, that's impossible. You can't knock down more pins than there are available. So that's going to be given a probability of 0. If x is less than or equal to n, then it evaluates this thing here, which is just what I said before on the previous slide, the xth Fibonacci number divided by -1 plus the nth plus 2 Fibonacci number. And so I have that function. I have a sample space that's comprised of the integers between 0 and 10 inclusive. So that's what the colon does in R. And if you just evaluate that function across the sample space omega, you get these values here, the first, all these. So you can see these numbers are non-negative. In fact, they're all positive. And they're between 0 and 1, which is a characteristic of probabilities. But importantly, the sum of the probabilities evaluated over the entire sample space omega sums to 1. And this is really the characteristic property of these probability functions, that something in the sample space has to happen, and nothing outside of the sample space can happen. Otherwise, you've misdefined your sample space. So this is, if your probabilities don't accumulate to 1, you've done it wrong. And if your probabilities do accumulate to 1, then it's very hard to be wrong. You have to sort of actively try to do something wrong and nevertheless get probabilities that accumulate up to exactly 1. So that is achieved here. And then in the last line, I use the sample function that comes with R. And the sample function allows us to take a realization or multiple realizations from any finite set. So we put in the set as the first argument. We say size equal 1. We want one random draw from the set. And then the third argument to the sample function is the probability. So we need to give it a vector of probabilities that correspond to each element of the sample space omega. And then R is able to randomly draw a value from that sample space, and we'll assign that to the symbol little x. That's one realization from the sample space omega, or we can think about it in this case, one realization of a first roll of a frame of bowling. And that's some number of pins knocked down. Randy.
Here's an obviously greatest number, 7. So assuming that somebody is bowling or something.
Yeah. Well, the highest number is actually for a strike. It's 0.384.
You're right.
Yeah. So this is applicable if you wanted to do it substantively for like a decent bowler, probably not a professional bowler, but maybe someone who bowls in like a league or something like that.
So is that built into the trying to function? Is that built in someplace, or is it
It's kind of a property of Fibonacci numbers. So this is, they're increasing. So the least possible thing is the gutter ball, and the highest one is the strike, and they increase from that. So that does reflect that you have at least a little bit of skill. Yes. Oh, the golden, you can look at it on Wikipedia. It's just defined as 1 plus the square root of 5 over 2. It's something that like mysteriously appears in math everywhere. There's lots of things in math that are called the golden something. Yeah, it appears with the Fibonacci numbers and a bunch of other things. It's just one of these numbers that keeps popping up. It's transcendental or irrational or whatever. Anyway, it's just a special number. Don't think too hard about it. So does everybody understand this? And for those of you who had R, were able to load in these functions? If it didn't work, they're on Canvas. Awesome. Questions? Okay. So now let's think about the, so for those of you who have R and have gotten down to the last line where you take a realization little x from the sample space, what did you roll? So what's the value of little x? 9. Very good. Somebody else? You got 10. Even better.
10.
Also good.
So got 10.
10. So 10 is going to be a common number. But different people could get different things because this is a random variable. It comes up, with some probability. So for those of you who got less than 10, what would you compute the probability of picking up a spare, which is to say knocking over all the remaining pins after your first roll? How would we think about it in terms of the functions that we've defined? Yeah.
So first we got 9 would be x is 1 and n is 1.
Right. So n would be 10 minus x1. And then for the second roll, you can evaluate the function with either 0 or 1 for the first argument x, which is now going to pertain to the second roll, and then the background argument n 10 minus x1. And so x1, the realization of it appears in the definition of the probability function for the second roll as n equals 10 minus x1. So how will we compute the probability of getting the spare? So let's define two random variables, capital X1 and capital X2, to be the number of pins knocked down on the first and second roll. How would we compute the probability of knocking down X2 pins? So for that, we can evaluate the Fibonacci in the numerator at X2, and in the denominator, it's -1 plus the Fibonacci number evaluated at 10 minus X1 plus 2. We also have to have the restriction. So this I business is what's known as an indicator function. It returns 1 if the condition inside it is true, and it returns 0 if the condition inside it is false. This is necessary, so we can't have a situation in which like X2 is 7 and X1 is 5. Or if we did, we want to give probability 0 to that because it's, outside the rules of bowling to knock over 12 pins in one frame when there's only 10 available to start with. So kind of a little technical detail. Let's think about X2 as being 0 deterministically if you get a strike on your first roll of a frame of bowling. So if you get 10 on the first, the second roll doesn't actually happen. But if it did, you're guaranteed to knock down 0 pins on the second roll because there's no pins standing up. You'd just be rolling a ball into the abyss. So that's going to be conditionally deterministic. If you get a strike on the first roll, the second roll becomes conditionally deterministic. And this setup where we have the probability of, X2 being this or that, given that the random variable X1 is equal to the realization little x1, is known as a conditional probability function because it has as part of its definition the realization of another random variable. And we need to condition on knowing what happened on the first roll in order for us to say anything about the probability of knocking down X2 pins on the second roll. So conditioning is something that is really fundamental, especially for Bayesian analysis, and it basically means sort of restrict your attention or do your operation only in the subset where the condition holds. So if 9 pins are knocked down on the first roll and we're thinking about a probability function for the second roll, we only have to worry about the case immediately in front of us where we can condition on the fact that the random variable for the first roll was realized to be 9 or 4 or whatever it may be when computing that probability knocking down X2 pins on the second roll. Is that clear to everybody? Okay. So we talked a little bit on Tuesday about probability as sort of being a generalization of Aristotelian deductive logic. And we said that in R and a lot of other language, true is sort of treated as 1 and false is treated as 0 when doing arithmetic operations. So true and true is equal to true times true, and true and false is equal to true times false. Those both come up true. And we can generalize this idea to probabilities that are interior to the 0-1 interval to compute the probability that 2, and if we can do it for 2, we can extend it to 3, 4, 5, etc. Propositions are true simultaneously. And for that, we need what's known as the general multiplication rule, which can be written with this sort of upside down U symbol, which gets read as and. So the general multiplication rule states that the probability that the first random variable A takes a particular value and another random variable B takes a particular value is equal to the probability that B occurs multiplied by the conditional probability that A occurs given that B has occurred. Or you can write it the other way around. It's the probability that A occurs multiplied by the probability that B occurs given A. Now, you can extend that to the Aristotelian case, but in the Aristotelian case, things are sort of true or false irrespective of any other random variables. And so the conditioning thing doesn't really come into play. But talking about probabilities that are interior on the 0-1 interval, the way to do this in a mathematically valid way is to take the probability of one thing, multiply it by the conditional probability of the other thing, given that the first thing occurred. And that yields us the probability that both A and B are true, or both A and B happen. And that's what's known as the general multiplication rule. You can think of it as really sort of an axiom of probability from a Bayesian perspective. Yes?
The second one, false.
Right. So true and false is false. But true and false is the same as true times false. So this is false and that's false. And it's true that false is false. Even more true is the general multiplication rule. And we're going to be using that as we go along. Questions? So the general multiplication rule helps us clarify the concept of independence. So loosely speaking, two random variables A and B are independent propositions. If whether A is true or false gives us no information at all about the probability that B is true and false, or false, and vice versa. But more rigorously, A and B are said to be independent if and only if, so that's what IFF means, the probability of A given B simplifies to the probability of A irrespective of B, which is to say B doesn't appear in the formula for the probability of A, and conversely, the probability of B given A simplifies to just probability of B. You don't need to include A in the formula of that. And if A and B are independent, then the general multiplication rule is going to simplify to a special case. The probability that both A and B occur is simply the probability of A multiplied by the probability of B, because the fact that we've assumed they're independent means the conditioning provides no information about the other random variable. So let's see if we can apply this. Why might it be reasonable to think that two rolls in the same frame of bowling are not independent of each other? Yeah.
Because how much you roll for the first one affects the number in which you can hit in the second one.
Right. So x1 explicitly appears in the probability formula for x2 via n, because n just gets substituted to 10 minus x1. So it explicitly shows up in the formula. Those are not independent. But why might it be reasonable to think that two rolls in different frames of bowling are independent? Ready? Yeah. So irrespective of what you do in the first frame, you're going to get 10 pins in the second frame to knock down in every other frame as well. So at least as far as the rule goes, there's no rules of bowling go. There's no dependence between, different frames of bowling. But why might two rolls in different frames of bowling not be independent? I mean, they are in the formula that we assumed, but if we maybe elaborated it a little bit, what reasons to think consecutive frames of bowling might not be independent? Yeah.
Maybe if you perform poorly on the first one, you're a little bit nervous the second time around, low confidence, you hurt people for the next time.
Yeah, could get in the zone, could hurt your arm. Yeah, Rennie?
Same boulder. So bowling, fifth grade, same boulders.
Right. So we would need to condition on the ability of the bowler, which presumably remains constant within a game. And then conditional on that, maybe the second and fifth frame are independent of each other. But if you improve during a game or unimprove because your arm is hurt or something like that, then those could be reasons why different frames would not be independent. And then why might rolls of two different people, even in the same frame, be independent or not independent? Mm-hmm. Yeah, so they grease them up. So that might be a reason. If two people are rolling on the same bowling lane, then they might not be independent. But, you know, let's say they have different lanes. Then why might it be kind of reasonable to assume that those are independent of each other?
The performance of one isn't conditional on performance of another.
Right. Although, you know, if they go at the same time, one might distract the other or something like that. So you can think of reasons either way. But usually when specifying a probability model for something, you're going to have to assume, you know, some stuff is independent from some other stuff in order to simplify the calculations. And basically what that amounts to is assuming away all like little things that might induce like a small amount of dependence, just saying we're going to ignore those, like, you know, the temperature in the bowling alley or something like that could induce some dependence, but we're just going to ignore all that when simplifying things down for a model. Okay. So what would be the probability of obtaining a turkey, which is what happens when you get 3 consecutive strikes and the picture of the turkey pops up on the television? Using the formula that we used before.
The probabilities for a strike, right? We have to add those across it, or add prorate.
Now, if you add 0.384 3 times, you're going to get like 1.2 almost. That doesn't sound right. What you got? Multiply them. And in multiplying them, what have you implicitly assumed, even though it's perhaps reasonable? That they're independent of each other. First roll across 3 different consecutive frames, getting a strike, we're going to assume those are independent of each other, in which case it's the probability of getting a strike cubed. Everybody see how we did that? All right. So what would be the probability of knocking down 9 pins on the first roll of a frame of bowling and 1 pin on the second roll of that same frame? How would we compute that? What would we need to do to compute something like that? Yeah.
Multiply the probability of throwing nine pins with the conditional probability.
When there's 1 remaining. So we need to multiply the probability for knocking down 9 on the first times the probability of knocking down 1 on the second, given that there's n equals 10 minus 9 or 1 pins standing up for our second roll of bowling. And that gives us the joint probability of a 9 and a 1. Those 2 things together. And that's just applying the general multiplication rule. Does everybody understand how we got that? Okay, so in general, how we obtain the probability of knocking down x1 pins on the first and x2 on the second, we can write that as the probability of the first times the conditional probability of the second, given that x1 pins were realized to be knocked down on the first roll and that we started with 10. So that would be what we had before, the probability for the first roll multiplied by the conditional probability of the second roll. And again, we have this indicator function, so we make sure that we're assigning probability 0 to anything that entails knocking down more than 10 pins in a frame of bowling. And we can represent that with a couple loops in R. So first I'm going to make 11 by 11 matrix to represent the joint probability of knocking down X1 pins on the first roll and X2 pins on the second roll of the same frame of bowling. Then I loop through the elements of the sample space, pull out the probability of knocking down X1 pins on my first roll, and then I do an interior loop for my second roll. So that only has to go from 0 up to 10 minus X1. And then I'm going to stick in the appropriate cell of my 11 by 11 table the joint probability of that happening by multiplying the probability of knocking down X1 pins on the first roll by the conditional probability of knocking down X2 pins on the second roll, given that there are 10 minus X1 pins available to be knocked down. And when I finish going through those double loops, if I've done things correctly, my table for the joint probability of knocking down X1 and X2 pins in the same frame of bowling should indeed has to sum to exactly 1. And it does, because I've done it, consistent with the general multiplication rule. Randy? They're actually not characters. They're integer values, but I put row names and column names so that when you see it next, the row is going to correspond to how many pins you knock down on the first roll, and the column for how many pins you knock down on the second roll. So the interior cells of this table tell you the probability of knocking down row pins on the first roll and column pins on the second. The intersection of those is going to give you a cell and a probability in that cell.
So those are numbers.
Yeah. So this set of filling in the loops yielded me this table. So why do I have all these zeros in the bottom right of my table? Right, they're not possible. So it's not possible to knock down 8 pins on the first roll and 5 pins on the second. So I just, in order to keep the table square, I fill in all those zeros, but those are never going to happen. And then in the sort of top triangle, we have numbers. They're small numbers. They're numbers between 0 and 1, but they're greater than 0. And so there's going to be positive probability for each of the 66 things that could happen across 2 rolls in the same frame of bowling. I could get a 1 and a 2 or a 3 and a 7. Anyway, there's like 66 possibilities that could happen 2 rolls of the same frame of bowling that have positive probability, and the sum across the upper triangle here is going to be exactly 1, which is what we established before. Yes. You don't need to keep copying this in, but if you want to, you can. Questions about that? Yes.
What's the X1 plus 1 and X2 plus 1?
Right. So R starts numbering with 1,
Oh, okay.
but bowling starts numbering with 0. So everything is shifted by 1. So the first element, the first column, corresponds to 0 on the second roll. And so that's why I put the character version of the pin values in the column headers and the row headers. But yeah. Did you get it? Okay. So one of the things that we're going to learn as we go along is that a lot of probability computations, when they get difficult or perhaps even impossible, can still be managed by utilizing sampling with a random number generator, like we did before, using the sample function. And so the stochastic or the random number analog of the general multiplication rule is what I call composition. So a way in which you can draw from the joint probability distribution of x1 and x2 is first to randomly draw a realization little x1 from the probability function for the first roll of a frame of bowling, and use that realization of little x1 when you then draw a random realization of x2 according to its definition. And if you do that, first draw from the first distribution and use that when you're drawing, use that realization to condition on, when you draw from the second distribution, you're going to get a sequence of random draws that conform to the distribution that you've defined for the two variables x1 and x2. So you can see that with a loop here. I'm going to do this like a million times. I draw a first roll, x1, from the sample space using those probabilities. Then I draw little x2 from its conditional probability distribution, conditioning on the realization of little x1 that just happened via n equals 10 minus little x1. And I'm going to, you know, if x1 is 9 and x2 is 1, I'm going to increment my yes symbol. And after I've done a million realizations of that, if I take the number of yeses and divide by s, which is the number of simulations that I did, that proportion comes out to 11.8 something. And the so-called true value that I obtained for the probability of that happening by evaluating my joint PR table for 9 pins on the first roll, 1 pins on the second, is more or less exactly 0.1185, etc. But in the limit as s approaches infinity, as the number of simulations that I do gets larger and larger, this process is going to converge to the true probability of knocking down 9 pins on the first roll and 1 pin on the second. In this case, it's much easier for me to do it directly by just looking up the value in the table, but we'll quickly escalate into situations in which it's not even possible to do that calculation. But it is possible to do simulations from random numbers, and if we do a lot of them, we can approximate these probabilities that we need with as much accuracy as we want, just by setting S to be sufficiently large. So does everybody see how drawing from the first distribution and using that when drawing from the second distribution is sort of analogous to the general multiplication rule, where you multiply the probability of the first thing by the conditional probability of the second thing given the first thing, in the usual case when those two things are not independent of each other. Does that make sense? All right, so we're going to be relying on simulation after the first couple weeks. So what would be the probability that you fail to get a strike on this frame or the next frame? How would we think about what that is? I want everybody to have a chance to think through that. Yes, you can. Or a shortcut to that would be 1 minus the probability of getting a strike. So we said that was probability to strike is 0.384 something. So 1 minus that would be 0.62 something. Okay, but what we want is what's the probability that we fail to get a strike on this frame or the next frame? Square. Right. So if we wanted the probability that you fail to get a strike on this frame and you fail to get a strike on the next frame, then we would use the general multiplication rule, even though those two frames are independent. But the question that we're looking for here, what's the probability to fail to get a strike on this frame or fail to get a strike on the next frame? Not and, but or. sum the probabilities. So we said 1 minus 0.38 was 0.62 something. And if we add 0.62 and 0.62, we get 1.24. And then minus the probability that both occur. So in order to figure out the probability of failing to get a strike on this frame or the next frame, we need to take the probability of the first thing, add it to the probability of the second thing, and subtract the probability that both happen. So the so-called general addition rule, that involves the big U-shaped thing, which is read as OR, is define the probability of A happening or B happening is the sum of the probability of A and the probability of B minus the probability that they both happen. And that subtracting piece is what ensures that the probability of A or B remains between 0 and 1. You can show that. But in a lot of cases, the probability that A or B, or the probability that A and B occur is 0. So for example, for the same roll of a frame of bowling, you can't knock down 2 and 7 on the same roll. So the probability of that both happening is 0. And when the probability of two things happening is 0, we say that A and B are mutually exclusive, or you'll also see people equivalently use the phrase A and B are disjoint events. And that is, you know, reasonably common, but certainly for the question that's asked, what was the probability of failing to get a strike on this frame or the next? Those two events are not mutually exclusive, not disjoint. And so we have a positive probability that has to get subtracted off to use the general addition rule correctly. Is everybody with me there? All right. So what's the probability of knocking down 9 pins on the second roll of a frame of bowling if I don't tell you how many pins were knocked down on the first roll of that frame? What's the probability of knocking down 9 pins on the second roll, irrespective of what happens on the first roll? How can we compute that from our table of joint probability for something on the first roll and something on the second? Oh, were you raising your hand? No? Okay. Yes, thank you. Correct. So this element here, which corresponds to a gutter bowl on the first roll and 9 on the second, plus the probability of getting 1 on the first roll and 9 on the second for a spare. Those two events are disjoint because you can't knock down 0 and 1 on the first. So there's nothing to subtract for the third piece. We just add this and that. You get about 0.0026. Technically speaking, we could add all these zeros as well, but that's not going to change the number because those were impossible in the first place. Does everybody see how we arrived at that? So what's the probability of knocking down 3 pins on the second roll if I don't tell you what happened on the first roll? How would you, of the same frame, how would you compute that? Mm-hmm. Oh, you're raising your hand? No?
Me?
Yes.
Just the sum, following the same rational, just the sum, but under the 3 column.
Under the 3 column, right. So in general, how will we obtain probability of x2? Given that you start with n equal 10 at the beginning of the frame, but not conditioning on x1, irrespective of x1. The events in the first roll are mutually exclusive, so we get to use the easy version of the general addition rule to perform what's known as marginalization. And the reason why it's called marginalization, back in the old days, people used to take the column sums or whatever, and they would write them in the margin of a table like this. But it's just a way to obtain a probability distribution for the second roll that does not condition on the first roll. And we do that by taking the joint probability of the first roll and the second roll, given that you start with n pins, n equals 10 pins, which we can write that as a conditional probability multiplied by a marginal probability. And then we sum that over the possible things that could have happened on the first roll of our frame of bowling. And you can just see that in R, that, okay, my first roll here is just PR evaluated at all omega. We got those numbers that we saw before. And if I take the row sums of my previous table, that's going to give me the marginal probability of knocking down X1 pins on the first thing, which is exactly the same as what I got if I just evaluate my PR function. But if I take the column sums of my table, that gives me the probability of knocking down X2 pins on the second roll without conditioning on what happens on the first roll. And those are very different numbers. So the probability of knocking down 2 pins on the second roll, irrespective of what happens on the first roll, is a much larger number in relative terms than the probability of knocking down 2 pins on the first roll. So the marginal distributions in a frame of bowling between the first roll and the second roll are not the same, but we can define both of them relatively easily if we have a table of joint probabilities for all the things that could happen across the 2 rolls in a frame, and we marginalize appropriately. Does everybody see how, what corresponds to what and what doesn't here? Mm-hmm. Yeah, they're synonyms. Other questions? Okay, so let's see how these 3 concepts interrelate between marginal probability, conditional probability, and joint probability. Joint is sort of a general word for the probability distribution of more than one thing. In this particular case, when we talk about a frame of bowling, we're actually specifically talking about a bivariate probability across the 2 rolls in a frame of bowling. But joint is just kind of a more general word for the probability of multiple things and includes as a special case 2. So as we said before, we can compose a joint, or in this case, bivariate probability distribution by multiplying a marginal probability for the first thing times a conditional probability for the second thing. Or we can do it the other way around, even though that doesn't make as much sense with bowling. But using the general multiplication rule, either way, multiply a marginal probability by a conditional probability, and we get a joint probability. We can decompose a joint, in this case bivariate probability, by adding the relevant joint probabilities down the columns or across the rows, depending on which marginal probability we want. So we can decompose a joint probability distribution by adding over the possibilities and thereby obtain a marginal probability function. So we can get a joint by multiplying a marginal by a conditional, and we can get a marginal by adding a bunch of values from a joint. And we can obtain a conditional probability, if we didn't already have it, by dividing the corresponding joint probability of those 2 things happening by the marginal probability. And that follows from the fact that the probability of A and B occurring according to the general multiplication rule can be written as the probability of B times the conditional probability of A given B, or it can equivalently be written as the probability of A multiplying the probability multiplied by the conditional probability of B given A. So if these two things in the middle and on the right are equal to each other, I can just take the probability of B over here and divide both sides of it. So now the probability of B appears in the denominator over here, and we're left with the probability of A given B is equal to the probability of A times the probability of B given A divided by the marginal probability of B, presuming that the thing in the denominator is not 0. Otherwise, B is impossible. And so the probability of A given B is not a well-defined thing if we're conditioning on something that could never be realized if the probability of B was 0. But in general, the probability of B is going to be greater than 0. And so we can write probability of A given B as the joint probability in the numerator divided by the marginal probability of B in the denominator. Randy, you had a question about that? Okay. Anybody else have a question about that? So these are three very important linkages between three very important concepts: marginal, conditional, and joint probability. So we can get a joint by multiplying a marginal by a conditional. We can get a marginal from a joint by adding down the columns or adding across the rows to obtain the corresponding marginal probability that we want. And we can obtain a conditional probability that we didn't already have by taking the joint probability and dividing it by the marginal probability that we want to condition on to give us an expression on the left-hand side that's equal to the thing on the right-hand side here for the probability of A given B. And this is what's known as Bayes' rule. Follows rather simply from the general multiplication rule, but it took until the mid-1700s for anyone to figure that out. And even still, no one knew until after Thomas Bayes had died, but, you know, anyway. Questions about those? So what number, or how would we arrive at a number for the probability of knocking down 3 pins on the first roll, given that 4 pins were knocked down on the second roll in the same frame of bowling? So you can think about this as like a missing data problem. And the Bayesian approach is really the only one that's appropriate for dealing with missing data, which is so common in the social sciences and a lot of other things. So say you walk into a bowling alley and you hear someone say, I knocked down X2 equal 4 pins on the second roll of my frame of bowling, but you didn't see what happened on the first roll of a frame of bowling, that frame of bowling. How could you use what we've been talking about today to compute the probability that 3 pins were knocked down on the first frame, even though you didn't see those? How would we do that?
So it would be the probability of A, which in this case is rolling a 3 in the first roll, times the probability of getting a 4 in the second, given that you rolled a 3 in the first, divided by the probability of getting a 4 in the second.
Right. And where would the probability of getting a 4 in the second come from?
From the margin.
Yeah, summing down the column
Sum of the column.
under 4.
Right.
Right. So that's using Bayes' rule to get the probability for the missing data. Maybe another or perhaps more colorful way, and perhaps because it took me like an hour to get 3 different colors into this table, we can see it. So the same numbers just with different colorization. So as we said before, the sum of the whole table is 1, and it has to be if we're doing probability correctly. But someone told you that they knocked down 4 pins on the second roll of a frame of bowling. So everything in blue could have happened, but didn't. Everything in red can't happen. So what we're left in black is the joint probability of 0 and 4, 1 and 4, 2 and 4, 3 and 4, 4 and 4, 5 and 4, and 6 and 4. That's all that's left. And so these small numbers here in the fourth column of our table are in the right proportion for a conditional probability, but probabilities, even conditional probability distributions, have to sum up to 1. And the fourth column clearly does not. It's much too small. And so what we have to do is take these values in the fourth column of our joint probability table and divide by 1 minus the sum of the blues. When we divide by 1 minus the sum of the blues, we divide the fourth column by 1 minus the sum of the blues. That bumps everything up. And now my conditional probabilities, given that 4 pins were knocked down on the second roll, sum to 1 again. But you might see that 1 minus the sum of the blues is just the sum of the black. So 1 minus the sum of the blues is the marginal probability of knocking down 4 pins. But I could get to that with less computation by just summing down the fourth column. And so that's how we could have arrived at an answer to this question. What's the probability of knocking down 3 pins on the first roll, given that 4 pins were knocked down on the second roll, knowing that you started with 10, but not actually seeing what happened on the first roll? Because if you saw what happened on the first roll, then you would condition on it. You could take it as given. But if you don't know it, you have to be able to say what the probability of it is according to your model of bowling and what you do know. They must have started with 10 pins, and they said, and we'll assume they're honest, that 4 pins got knocked down on the second roll. What are the implications of that for the probability distribution on the first roll? And we can evaluate that not just at 3, but at any number less than 6, less than or equal to 6. Questions about that? Have you actually crunched the numbers? Index joint probability by 3 and 4 and divide by the sum under the fourth heading, the marginal probability of knocking down 4, it comes out to 0.0322 or something. So what Bayesians do is generalize this. Again, bowling not interesting enough on itself. Really what we've been talking about today is more of a metaphor for something interesting, and to show how the rules of probability can be easily applied, or not so easily applied, but in any event applied to a situation that anybody can understand and think through, like bowling, before we try to apply it to harder situations that have like more possibilities and things like that. So what Bayesians do is generalize the usage of Bayes' rule by taking A to be your beliefs about whatever you don't know, and B to be whatever you do know, namely like data and things like that. And then, you know, plugging that into Bayes' rule in order to arrive at the probability of what you don't know given what you do know. And from a Bayesian perspective, that's really the essence of science. All kinds of things we don't know, but it'd be nice if we could get a probability for the things that we don't know being true or false or whatever, given what we do know that we arrived at by the data collection process. So that all seems pretty reasonable, except to frequentists. who accept Bayes' rule. I mean, they have to. Anything, any sort of rule or theorem of probability applies irrespective of whether you adopt the Bayesian, the classical, or the frequentist perspective on probability. So they can't really deny that Bayes' rule as written is valid because it just follows from the multiplication rule that also frequentists use. But they object to using the language of probability to describe beliefs about unknown propositions being true or false, and insist that probability has to be defined not as subjective degree of belief as to whether A is true, but as the property of a process that can be defined as the limit as the number of trials goes to infinity, the proportion of times that A occurs in S independent tries divided by S. So that definition of probability from a frequentist perspective doesn't involve anyone's beliefs, but it is a very limiting and narrow definition of probability that seems to only apply to processes that we can at least imagine being repeated over and over and over again, and we can observe the proportion of times that happens. Of course, from the Bayesian perspective, if you actually could repeat something like 1,000,000 times, the proportion of times that A occurs is going to be like almost exact. You should believe that's what the probability. And so, you know, it's always sort of a question of a degree. But if you don't have the opportunity to observe things over and over again, you maybe observe things at most once, you know, you still might be in a position where you want to organize your beliefs about the unknowns in a way that is consistent with the rules of probability, especially Bayes' rule. But Bayes' rule pretty much just follows from the general multiplication rule. So I ask you, what's the probability the Patriots beat the Rams in the Super Bowl next Sunday? That probably shouldn't seem like a crazy question to you. Indeed, there's all sorts of people on television talking about that very probability or what they believe that probability is. But none of the people that you see on television are frequentists. Frequentists only exist in sort of narrow academic confines. But if you were to take a strict frequentist perspective, it's impossible and indeed inappropriate for you to talk about the probability the Patriots beat the Rams in the Super Bowl, because that's not something that is going to be repeated over and over and over again S times. They're going to play the Super Bowl this year once. So this question can't be answered objectively and shouldn't be answered subjectively. But that doesn't stop millions of people from trying to arrive at an answer at it subjectively. And it doesn't stop tons of people from betting tons of money on one team or the other winning the Super Bowl. So one way to sort of understand probability from a Bayesian perspective is by actual or hypothetical betting. So do you, or would you be willing to risk $6 in order to win $4 if the Patriots beat the Rams? So if the Patriots win, you are +4, and if that should be Patriots, and if the Rams win, then you lose 6. If you're willing to take that bet, then the probability that the Patriots winning in your mind is greater than 0.6, or you're just like lighting money on fire. So the odds of an event is defined as the probability that it happens divided by the probability that it doesn't happen. So if you put, 0.6 in the numerator here and put 0.4 in the denominator, then the odds of that, if those are better than what is offered by your New Jersey sportsbook, then it's rational for you to take that bet. And if you think, you know, there's less than a 0.6 probability that the Patriots are going to win, then it's rational for you to bet at least a small amount of money, if we don't have to worry about risk aversion or anything like that, on the Rams, even if you think the Rams are not the favorite. If you think the Rams have less than a 0.5 probability of winning, but you might still be rationally induced to bet on the underdog if you think the probability of them winning is close enough to 0.5 that you sort of stand to gain more than you lose when you weight those by the corresponding probabilities. Pretty much, yeah. Or really, what defines rationality from the Bayesian perspective? So deciding what to do, you need to, you know, take a weighted sum of things that could occur using the probabilities as weights. And those probabilities should be the probability of what you don't know given what you do know. We know, we've seen, you know, lots of plays and lots of games of the Patriots and the Rams. There's all kinds of data you could collect in order to arrive at a probability that one or the other is going to win the Super Bowl. And, you know, you could do some Bayes rule stuff to try to figure out what you believe. And then if you get attractive odds, then it's rational for you to bet, you know, one way or the other. But just to back up a little bit, if you overhear someone on Broadway say, you know, they think there's a probability the Patriots are going to beat the Rams as being 0.6 or greater, you know what they mean. You might disagree, but there's no like deep mystical meaning or confusion about what somebody who says something like that is expressing. And if that's, you know, a well understood vocabulary for football and a lot of other things, why does science have to be different? Why do we need a completely different perspective on probability in order to do science? Why do we need to do what the frequentists insist have to be done? Defining probability as the limit, is the proportion of times that something happens if the number of trials is repeated over and over in that limit, when everything that we experience in the real world is going to be done like once or a small number of times, really. And so that definition doesn't seem to apply, and yet frequentists oppose the Bayesian move to open that up, to generalize the applicability of Bayes' rule to describing our beliefs in light of a finite amount of information that we can condition on. So that's one of the things that we'll have to come back to over the rest of the semester, these different perspectives on how probability should be defined and how it should be used. But irrespective of the perspective of probability, interpretation of probability that you take, the rules of probability apply the same way. So conditional, marginal, joint, independence, all those concepts that we talked about today continue to hold just as a matter of logic. Okay, so get on Campus Wire, post some questions, do the reading for next week. We'll continue to talk about other aspects of probability with discrete random variables, and just continue on like that.